Okay, I want you to picture a scenario. You've been hired to take a portrait.
Right.
And it's not just any portrait, it's a high-resolution macro shot of a hummingbird in mid-flight.
Okay, so a standard National Geographic assignment.
Exactly. You need to capture the iridescence of the feathers, the wing flutter, the whole 9 yards.
Oh, got it.
But here's the catch. The camera you have to use is the size of a minivan. It makes this rhythmic screaming noise that's louder than a jet engine,
Oh.
which obviously terrifies the bird. And just to make it impossible, the only way the camera can actually take the picture is if the bird is clamped inside of it.
Wow.
Oh, and if the bird chirps. The vibration shakes the lens, and the photo is just a useless smear.
You know, usually analogies in science are a little bit of a stretch, but that is uncomfortably accurate.
Right.
You've basically just described the central paradox of modern neuroscience.
That's exactly where we're going today. We are doing a deep dive into a very specific, very frustrating engineering problem: functional neuroimaging of speech production.
Or, to put it simply, how on earth do you take pictures of the brain speaking when the act of speaking literally breaks the machine?
It's the ultimate observer effect. To study the thing, you have to do the thing, but doing the thing ruins the measurement of the thing.
Precise.
And to help us navigate this whole mess of magnets in motion, we are unpacking Chapter 5 from the Handbook of Psycholinguistics, the 2nd edition.
It's called Functional Neuroimaging of Speech Production by Thomas Zeffiro and Jennifer Freimure.
And honestly, this didn't read like a textbook to me. It felt more like a manual on how to hack the human body.
That's a really good way to put it.
Yeah.
It's basically a detective story about how researchers went from using radioactive gas to leveraging the sluggishness of our own blood flow just to get a clear picture.
Before we get to the hacks, though, let's establish the stakes. I mean, why do we even care? Why go through all this trouble?
Well, because for a long time, we were just flying blind. If you wanted to understand where language lived in the brain, you basically had to wait for a tragedy.
A stroke or a head injury.
A stroke, a tumor, yeah.
Right.
And then you document what the person couldn't do anymore.
The learning by subtraction method.
Right. Oh, this patient lost the ability to name animals, so that damaged spot must be the animal naming spot. It was retroactive, imprecise.
But functional imaging, it promises regional functional specialization. It lets us see the brain lighting up in real time, non-invasively, in healthy people.
It's the difference between looking at a map of a city after an earthquake versus watching traffic flow during rush hour.
A perfect comparison. We can see the neural architecture of the most uniquely human thing we do.
Communicate.
But, as my opening analogy pointed out, getting that view is incredibly difficult. The source points to two massive enemies. They call them the acoustic nightmare and the jiggle factor.
I think the text actually says acoustic noise and motion artifacts, but...
Yeah, but jiggle factor just feels more emotionally accurate, you know?
It really does.
Yeah.
It really does.
Okay, so we're going to get into the weeds of why fMRI, the gold standard of brain scanning, actually hates speech. But to understand the solution, we have to look at how we got here.
Yeah, we definitely didn't start with fMRI.
No.
No, we started with something much cruder. The foundational concept actually goes back to 1890 to a researcher named Roy.
And he's the one who figured out that neural activity is coupled with cerebral blood flow.
Which is the basis of almost all modern imaging. If a brain region is working hard, it demands more fuel.
Supply and demand.
Exactly. If you're trying to conjugate a verb, the part of your brain doing that heavy lifting needs more oxygen, more glucose, so the body flushes that area with blood.
So if you can track the blood, you can track the thought.
That was the idea. And the first attempts to track that blood were adventurous.
That's a very polite way to put it. We're talking about SPECT imaging in the 70s and 80s.
Right. And to get the map, they use 133Xe.
Which is radioactive xenon gas.
Yes. They had subjects inhale radioactive gas.
It feels very mad science. I'd assume the image quality wasn't exactly, 4K.
Oh, not even close. Far from it.
Right.
We're talking low resolution, blurry, basically 2D. But it did the job. It confirmed language was lateralized. That happened mostly in one hemisphere. It proved the concept worked.
And from there we moved to PET scans, positron emission tomography.
Which was a huge leap. Instead of gas, they were using H2NCOO radioactive water. And this gave us a much better look at regional cerebral blood flow.
Okay.
And here's the interesting part, for our topic anyway. PET was actually pretty good for studying speech.
Really? I just assumed newer machines were always better.
In resolution, yes.
Mm-hmm.
But the environment, PET was great. The scanner is a silent observer. It doesn't make noise. And more importantly, the camera isn't overly sensitive to the jaw moving.
So you could just sit in a PET scanner, recite a poem, and the image would be stable.
Relatively, yes.
So why did we stop using it? If it works, why fix it?
It really comes down to safety. Because you're injecting a radioactive tracer, there's a strict dosimetry limit.
Meaning you can only get zapped so many times.
That's it. You can't just keep scanning the same person over and over to get more data. You get a few scans, and then you're done. You just can't run the complex, repeated trials we need for modern psycholinguistics.
Which brings us to the current king of the hill, fMRI, functional magnetic resonance imaging.
Completely non-invasive, no radiation. You can scan a subject 1,000 times if you want.
Yeah.
It uses bold D contrast.
That's BOLD, blood oxygenation level dependent contrast.
Right. It relies on the fact that oxygenated blood and deoxygenated blood have different magnetic properties. It's brilliant, it's safe, and for almost every area of neuroscience, vision, memory, motor skills, it's the best tool we have. Except for speech.
The source is pretty brutal here. It describes fMRI as being uniquely terrible for spoken language experiments.
It's a classic engineering trade-off. We got rid of the radiation, but we introduced a completely chaotic environment.
Okay, let's break down that first enemy, the noise. I think most people know MRI machines are loud, but the source gets specific about how loud.
It's not just loud. It's violent. The noise comes from the gradient coils vibrating. We're talking about sound pressure levels reaching 138 decibels.
For context, a rock concert is around 115, maybe 120. So 138 is like standing next to a jet engine. It's at the threshold of physical pain.
And it's not a white noise hum you can tune out. It's a narrow band, high-frequency screech that pulses 10 to 15 times a second. It's rhythmic.
So you're trying to study how the brain processes sound and speech while blasting the subject with a rhythmic jackhammer.
Yes.
That seems like it would mess with the data.
Oh, it messes with it in 3 distinct ways. First, obviously, is masking. If the experiment needs the subject to hear a prompt, the scanner noise might just drown it out.
Hard to study auditory processing when you can't hear the instructions.
Second is just distraction. Your brain automatically allocates resources to process loud, threatening noises. It changes your attention state. The brain you're scanning is a brain under siege, not a brain at rest.
But the third point the authors make is the most technical and I think the most important. It's about the subtraction fallacy.
This is a crucial insight. In neuroimaging, we often use what's called cognitive insertion. We scan you doing task A, say, looking at a blank screen. Then we scan you doing task B, speaking. We subtract A from B to find the speaking activity.
And the logic is that the scanner noise is a constant, so it cancels out. It's just background static.
That's the assumption. But the source argues it's completely false. The noise is so intense it creates a ceiling effect in the auditory cortex.
A ceiling effect.
Imagine your hearing is a bucket. The scanner noise fills that bucket to the brim. So if you try to pour a little more water in the experimental speech task, the bucket is already full. It just spills over.
So you lose the dynamic range. The brain can't register the difference because it's already maxed out.
Completely. The auditory neurons are saturated. They physically can't fire any faster. So when you do the subtraction, you aren't seeing the true difference. You're seeing a corrupted baseline.
That is a massive blind spot. And it implies a lot of early data might be suspect. But even if we could magically silence the machine, we run into enemy number 2.
The jiggle factor.
Motion artifacts. This is where the physics of MRI really clashes with the biology of talking.
You can't speak without moving. It's a physical act.
And the source breaks this down into 3 types of motion. First, rigid body motion.
The whole head moving.
Right.
Your jaw's attached to your skull.
Mm-hmm.
When you open your mouth to say hypothesis, your entire skull rotates and shifts, even if it's just a tiny bit.
And in fMRI, we're looking at voxels, these tiny 3D pixels. A tiny shift is a big deal.
It's a huge deal, and it creates what they call a rim artifact.
A bright ghost or halo around the edge of the brain.
Yes, it looks like brain activity, but it's just a false signal from the head shifting.
Then there's parenchymal motion, which I have to admit I didn't know was a thing.
The brain jiggles.
Inside of the skull.
Inside the skull. It's soft tissue floating in fluid. Every time your heart beats, every time you breathe, the brain pulsates. So the target is constantly moving.
But the third type of motion is the real killer for speech.
Articulator motion. The movement of the tongue, the jaw, the lips.
Even if we clamp the head down, the jaw has to move to speak.
And here's the physics twist. The air in your mouth has a different magnetic susceptibility than the tissue of your tongue.
Magnetic susceptibility. That's how easily something gets magnetized, right?
Roughly, yeah. It disturbs the magnetic field. When you speak, you're rapidly changing the shape of that air cavity in your mouth. This warps the magnetic field in the immediate area.
And unfortunately, the immediate area isn't your foot.
No, it's the medial and inferior temporal cortical regions.
The exact parts of the brain responsible for language.
Precisely. The act of speaking creates a magnetic distortion right on top of the anatomy you're trying to study. It generates false positives. You see a bright spot and think, aha, language processing. But it's just the magnetic field bending because the subject opened their mouth.
It feels like a trap. The machine is too loud to hear, and moving your mouth breaks the picture. So the obvious question is, why not just cheat?
Cheat how?
Why not just have the subject think the words? Covert speech. Just read silently. No jaw movement. Problem solved.
That was the hope for a long time. It would have solved everything. But the authors, they shut this down unequivocally.
They cite a specific study figure 2 in the text that compares overt, out-loud speech versus covert, silent speech.
And the results are clear. They're not the same thing. They engage different neural systems.
How different?
Significantly. Especially the inferior frontal gyrus, or the IFG. When you speak out loud, your brain is doing things it doesn't do when you read silently. It's planning motor movements. It's engaging auditory feedback loops.
You're listening to your own voice.
You're listening to yourself to correct pronunciation. All of that is missing in silent reading.
So if you study silent reading, you're studying silent reading. You aren't studying speech production.
Exactly. The neural map is different. If you want to understand how humans speak, the subject must speak. You can't just swap them out.
Okay, so back to the paradox. We need them to speak, but speaking ruins the data. This seems like a dead end. But then the chapter pivots.
It introduces a solution that's honestly just really clever timing.
It's a solution that relies on biology, not engineering. It's called interleaved acquisition.
And the key to this whole technique is something called a hemodynamic delay.
This is the big takeaway.
This is it right here. Neurons are fast. Electricity is instant. But blood is slow.
And Bull-D imaging measures blood, not electricity.
Exactly. When you say a word, your neurons fire immediately. But the body takes time to send the fuel. The blood flow response doesn't even start for about 2 to 5 seconds.
And it doesn't peak until 5 or 6 seconds after you spoke.
And it takes another 10 seconds or so to go back to baseline. It's like thunder and lightning. The neural firing is instant. But the thunder, the blood flow signal, it rolls in seconds later.
So scientists realized they could use that lag. They could fit the scan in the gap between the lightning and the thunder.
That's the interleaved part. You mix the behavior and the scanning by staggering them.
Okay, walk us through the steps. How does a scan like this actually look?
Okay, step 1. You turn the scanner's noisy gradients OF.
So the room goes quiet? No 138 decibel shrieking?
Relative silence, yeah. Step 2. The subject speaks. Because the scanner's off, there's no acoustic masking. And crucially, the magnetic field isn't trying to take a picture while their jaw is moving.
So the shutter is closed while all the jiggling is happening.
Exactly. Step 3. The subject stops speaking. Their jaw is still again.
But inside their brain, the blood is just now starting to rush to the language centers.
The thunder is rolling in. So, step 4. Turn the scanner on. Snap the picture.
That is just incredibly elegant. You capture the signal after the noise and the motion have stopped, but while the evidence is still fresh.
It neatly sidesteps almost every single problem we've been talking about.
It feels like using the body's own inefficiency, its slowness, as a tool.
It is. But, like everything in science, there's a cost.
Let me guess. Time.
Time. In a standard scan, you're taking pictures constantly, maybe every 2 seconds. You get a mountain of data. In this interleaved method, you have to wait for the quiet period, the speaking period, the delay. You just end up with fewer data points per minute.
So your statistical power goes down.
It can, yeah. It takes longer to build a reliable map. You might need to keep someone in there for 45 minutes instead of 20, but the source argues the trade-off is absolutely worth it.
Quality over quantity.
1,000 blurry pictures are worth less than 1 sharp one. This method produces activity maps that are just clean. It's how they've been able to confirm all those differences in the IFG we talked about.
It's amazing that the breakthrough didn't come from building a quieter machine, but from understanding the timeline of the brain itself.
Sometimes the best engineering solution is just looking at the biology and saying, hey, we have a 5-second window here, let's use it.
So is this the end of the road? Or is there a next big thing coming?
The field is definitely still evolving, and the source hints at what's coming next, which I think is really exciting.
Active noise cancellation.
Yes. The same stuff we use in our headphones on airplanes. Engineers are trying to build it directly into the magnets themselves.
To cancel out that 138 decibel scream at the source.
If they can do that, if they can make a truly silent fMRI, we won't need the interleaved trick anymore. We could just scan continuously without that acoustic nightmare.
Which brings up a provocative thought to end on. If the camera has been so loud for so long, what have we missed?
That is the question, isn't it? We know the noise saturates the auditory cortex. We know it changes your state of attention.
So if we could look at a brain in total silence, what subtle whispers are happening that we've just never seen before?
There could be low-level auditory processing, faint feedback loops, emotional responses that have been completely drowned out by the gradient coils for the last 30 years.
A whole layer of brain activity just hidden by the noise of the tool we use to find it.
I might have to rewrite a few of those chapters in the handbook.
I love that idea. Science is never finished. It just gets a better camera.
Couldn't have said it better myself.
Thanks for taking this deep dive with us into the noisy, jiggly, paradoxical world of speech neuroimaging.
Always a pleasure.
To our listener, keep asking questions, keep thinking about the how behind the science, and we'll catch you on the next deep dive.